So good morning everyone and welcome to this special lecture, circular motion. Well, I have broken the trend. Normally I teach circular motion somewhere after Newton laws of motion. But here, since we have less time, I can't teach the same topic twice. So I'm just taking it before rotation motion. Now remember, I might use the word rotation because rotation and circular motion, the equations in some sense are going to be same. So some question I might give you from the rotation wala chapter, that doesn't make any difference. It is all circular motion. Though rotation is not same as circular motion, the equation though are. Now, as soon as we start this circular motion, the first thing you have to understand is what do you mean by a circular motion? What do you mean by circular motion? What do you mean by circular motion?
A particle moving in a circular path.
Particle moving in a circular path. Well done. What do you mean by a circular path? What do you mean by a circular path? What do you mean by a circular path? So, if a particle is moving in such a way what? That it's, see, every circle has a center and every circle has a radius r. Now, how do you define this or how do you write this circular motion? If any particle is moving in such a way what? Any particle moving in such a way that what? Its distance from a fixed point. This is only applicable for circular motion. When we come to rotation, something might change. That is distance from a fixed point remains what?
Same, constant.
Remains same or constant. Then we say that it is moving on a circular path. What is that fixed point known as?
Center.
That fixed point is known as the center, and that fixed distance is known as the
Radius.
Of the circle. Or in short, if you know maths, you know circle. Any particle moving on a circle, we can call that motion as circular motion. In fact, if I say that even if a particle is moving in a straight line, we can imagine, see, any curve is a part of a circle from some point. Whenever you see any curve, any random curve that I draw, any random curve, any random arc that I draw, it is a part of a circle. Center lies somewhere. It has a radius of curvature as well. So anything that is not straight is curved. Anything that is curved has got a center and it got a radius. We call it center of curvature and we call it radius of curvature. So we'll see those terms also. Right now, let us just concentrate on something which is exactly circular. Circle. Now, once we understand this definition of a circular motion, the next question that comes is why we are studying it as a separate topic. Why we are studying it as a separate topic. If you remember in the 1D motion and 2D motion, we had done question where particle was moving on a semicircle or a circular path, and we found out what is the displacement, what is the distance traveled. We had actually done it using our previous 1D and 2D motion. Why now we need something different to, or why do we need a different heading for circular motion? Why do we need a different heading? Why do you have to study it separately? Let us say that this is a circle and a particle is moving on this circle. Now you can obviously make your x and y axis and you can have an origin. Now even if someone is moving on a circular path, let us say that he is at a point P at some point. If I ask you, how will you identify the position of this particle, you say, sir, not a problem. I will just draw perpendicular like this. It will give me the x coordinate. I will just draw perpendicular like this. This will give me the y coordinate, and I can straight away say that the position of this particle is xy. I don't need anything special. You can just do it this way. Yes, you don't need anything special. In fact, you can also draw a straight line like this, and you can draw the vector r, and you can write this r vector as xi plus yj. Yes or no?
Yes, sir.
You can write it like this, or now you can also write it like this. R vector is r cos theta I. Understand how I'm writing it? Plus
R.
r cos theta j. I can also write it this way. Nothing new. We have seen this, right? If I call this angle as theta, yes or no? I
Yes,
can
sir.
write it as r cos theta I plus r cos theta I plus r sin theta j. Yes or no? Now you can obviously write it like this. When what is the need of studying this differently? Let me just take this off. So I just don't want to introduce theta here. What is the need? So I can just write it like this. R can be written as r vector can be written as xi plus yj. There is no need to study circular motion differently. But if we understand one thing, and what is that one thing that we have to understand? We can obviously define your circular motion or find out your circular motion in this way, but I can also do it in a different way. See, this is again my x-axis, this is again my y-axis, nothing changes here. This is again my origin O, this is my radius R. Now, if I know that this particle is obviously always going to move on a circular path, now instead of giving its coordinates in terms of x and y, I can give them in a different way. The different way comes from the same r vector. I can draw a line like this, and I can tell you the radius of this circle is r. So the distance of this point from the origin O or the center O will be going to be r. Now, instead of telling you the x and y coordinates, I can tell you this angle theta. Now I know whether whenever this particle is, it is always going to remain on the circle. It will not go anywhere from here. It will always remain on the circle. So why should I tell you x and y always? Because at different points we can understand both the values of x and both the values of y will keep on changing. I can tell you the position of this point in a different way. To tell you the position of this point, I can tell you the radius of the circle, and I can just tell you this angle theta. Now, if I tell you in this way, r is going to be same for all the points. The only thing that will change will be theta only. So instead of two coordinates changing, x and y, both are changing for all the points, I can explain this and I can understand this in a different way where only one of the coordinates, theta, is changing. The rest of the thing r remains same for all the points. When I represent this in this way, this angle theta tells us the position of the particle. Yes or no?
Yes, sir.
When I represent this P in this form, where P is given in the form of r and theta, r being the distance from a fixed point and theta being the angle, this type of representation is known as the polar coordinates or polar representation. So I'm representing the point P in terms of polar coordinates. This type of representation is known as rectangular presentation. I am presenting in the form of x and y. Both are similar. But here we can see, in case of the right one, we have a distinctive advantage. Instead of giving you r and theta for all the points, I can give you r for all the points. R is same for all the points. I can just tell you the value of theta. This theta is known as the angular position of the particle in circular motion. It's applicable to circular motion. You can also do it for any other motion, but for any other motion, this may not be so good. This may look very awkward and very different and very confusing. But for circular motion, this becomes very simple. Physics, we are trying to make things simple and not trying to complicate things. So we are going to use this theta whenever we think about circular motion or rotation motion, because it is easier to imagine this motion in terms of this angle. Because things rotate, they rotate by an angle. Things turn, they turn by an angle. So it is easier to understand it in terms of this angle. And this angle or this theta is known as the angular position of the particle. Do we understand this?
Yes, sir.
Now, the point P is here. I can give the angle like this. If this point S, now the angle would be calculated in this way. Let me call this angle as phi. Remember, we can say this angle from any axis. We can say it from plus x, plus y, minus y. But the convention says that we must always say this angle from plus x axis. And also, if the angle is anti-clockwise, it is taken as positive. Anti-clockwise angles are positive, and clockwise angles are taken as negative. That is the sign convention we use. Do you understand the sign convention?
Yes, sir.
That is the first heading that we are going to write. And the first heading that we are going to write will be your angular position. Has everyone noted down this?
Yes, sir.
The first heading is angular position, denoted by the letter theta. What does this angular position give us? It gives us the position of the particle in terms of angle. The SI unit, it's radians because it's an angle. It is dimensionless because angle is dimensionless. I told you angle is the only physical quantity which is dimensionless, but it has a unit. It is dimensionless. It does not have any dimension. SI unit is radian. What type of quantity is angular position? Angle is a scalar quantity. So this becomes a scalar quantity. And we have this sign convention that we use. Anti-clockwise angles are taken as positive and clockwise angles are taken as negative. We'll also understand why it is so.
Yes, sir.
This is angular position. And normally we should give it from the positive direction of x-axis. Normally, but that's not hard and fast. Someone can tell me from some other axis, but that is how it should be. Angular position tells us the position of the particle. Do we understand this?
Yes, sir.
Now, as I said, the particle is moving in a circular path. It will always not remain at point P. It will keep on changing its point. Sometimes it will be on Q, some other times it could be on R, then it could be on S. So basically it is changing its position. Whenever it changes its position, it changes the angle. And we now have the next term coming in. What is the next term?
Angular velocity.
Hmm?
Angular velocity.
Angular displacement.
Displacement. Position.
Angular displacement. Delta theta. What will be angular displacement?
Change in Position of particle. Change in position of particle.
Change in angular position. Change in angular position. That is angular displacement. As soon as I say it is change in angular position, delta theta becomes theta 2 minus theta 1, where theta 2 is the final angular position, theta 1 is the initial angular position. The SI unit will be same as angle, radian. It is also dimensionless because it is the
angle radian.
difference between two angles. So it is again dimensionless. What type of quantity is angular displacement? Scalar or vector?
Vector quantity. Vector.
Large angular displacement. If the angular displacement is large, and when I say large, I will represent it by delta theta. Whenever I say delta theta, this delta theta is a scalar. This delta theta is a scalar. But if the angular displacement is very small, very small angular displacement, I write it as d theta. D theta is a vector. D theta is a vector. Why is that so? Find it out. Why is that so? Find it out. Why is large change in angle a scalar and a small change in angle a vector? Find it out. Okay. Now, as soon as I use the word angular displacement, and I've already used the word angular position, this must remind you of something that we have already done. This is known as your circular motion, or you can very vaguely say that it is also rotational motion. The other motion that we have studied till now was translatory motion. Circular motion is also translatory in that sense. We call it linear motion. Motion up till now was linear, and this is now circular. This angular position and angular displacement, does it remind of anything that we have already done? This angular position and angular displacement, does it remind you of something that we have already done? Nothing.
Sir, maybe the direction can be determined for small d theta.
No,
But-
I'm not asking the reason for that scalar or vector. I'm not asking that reason. You can find it out later on. I'm asking you angular displacement and angular position. Does it remind you of something? Or nothing?
Displacement and position.
If I take out this angular term out,
Displacement.
that is what it should remind you of. So whatever thing this displacement vector was doing in your linear motion, the only thing what was vector, this is for large displacement, for large angular displacement, it is a scalar. But apart from that, both the terms are similar. Displacement vector is used when the motion is linear, and angular displacement is used when we are talking about circular motion. Similarly, angular position Angular position is again telling us the position of the particle that was done by the gentleman. Which gentleman it was done by? The gentleman right here. This gentleman is doing the same job as this gentleman over here. Yes or no? Same thing,
Yes,
done in a
sir.
different way. That means this angular position is similar to what we had done, position vector. The only thing is one is a vector, one is a scalar. Do we understand this?
Yes, sir.
Angular position and angular displacement are similar quantities. No, angular position and angular displacement are similar to position vector and displacement vector. Yeah. Representing the same thing, but in angular sense, but in the case of circular motion. Do you understand this?
Yes, sir.
Having said that, now you should be able to understand what is the next term that is going to come.
Angular velocity, sir. Angular speed. Maybe the angular speed or angular velocity. Angular velocity, sir.
Average angular velocity. And we will write it dabba with an omega. This is not W, this is omega. Greek alphabet omega. Average angular velocity. What would be average angular velocity? Average angular velocity.
Angular displacement by change in time.
Time does not change. You don't call it change in time. Total angular displacement divided by total time. So I can write average angular velocity as delta theta by delta t, or I can write it as theta 2 minus theta 1 divided by delta t. What does this average angular velocity remind you of?
Average velocity.
This should remind you of average velocity. There is a difference though. Average velocity was a vector, but average angular velocity is a
Scalar.
scalar because it is angular, total angular displacement divided by total time, and total angular displacement is a scalar. SI unit?
Radians per second.
Radians per second. Dimension t minus 1 because radians does not have any dimension. Average angular velocity. Now this average angular velocity is always calculated over an interval of time between one point and the other point. It's always calculated over an interval of time. What is the next term that will come? Average angular velocity is calculated over an interval of time. What is the next term that is going to come? No one knows? No one knows. Instantaneous angular velocity. Omega vector. And this should remind you of linear velocity v vector. Instantaneous angular velocity. What would be instantaneous angular velocity? It is the angular velocity at any instant. If someone asks you, what is your angular velocity? You will tell your instantaneous angular velocity. You will not tell your average angular velocity. You will tell your instantaneous angular velocity. Instantaneous angular velocity, omega vector. And how will I find omega vector? Huh? How will I find omega vector? No idea, sir. This is the first time we are hearing this term. So how do we know? Yes. Fast. We don't have time. Huh?
Differentiation of angular displacement.
D theta vector by dt. As soon as we write it d theta by dt, it is the rate of what? Rate of what?
Rate of change of angular displacement.
No, it is not the rate of change of angular displacement. It is the rate of change of angular position with time. Angular displacement does not change. Angular displacement is already the change. So change cannot change. Rate of change of angular position with time. It has the same unit, radians per second. Do you understand it? So this is gone about saying bye bye, bye bye, bye bye, bye bye. I'm going.
Understood, sir.
Instantaneous angular velocity. What should be the next term that should come?
Average angular acceleration.
The next term that is going to come is
Average angular acceleration.
average angular acceleration. No, that is not the next term. The next term that is going to come is uniform
Angular velocity.
circular motion. Uniform circular motion. We call it UCM. Now, what do you mean by UCM? That is what you said. If the angular velocity remains constant, if the angular velocity of a particle moving in a circular path is constant, we call it uniform circular motion. What does this uniform circular motion? That means your omega vector is constant. Or you can say omega vector, since omega is a vector, its magnitude is always equal to average angular velocity. Average value and instantaneous value modulus magnitude would be same. What does this remind you of? Uniform circular motion where angular velocity is constant. What it should remind you of? Huh? It should remind you of uniform motion in linear motion. Uniform motion. When do we say the motion is uniform? When do we say that the motion is uniform? when velocity v vector is constant, your omega vector is constant. They cannot be same because when velocity is constant, the particle keeps on moving in the same straight line with the same speed. But when angular velocity is constant, it keeps on changing its direction. So motion wise, they are not same, but conceptually they are same. Do we understand this? Or just gone above what is saying bye bye? I'm going. I'm so confused. I'm going out. Conceptually, they are same. Uniform angular velocity means uniform velocity means velocity should remain constant. Uniform angular velocity means angular velocity will remain constant. But if you look at the motion, uniform velocity motion would be straight line with uniform speed. But uniform angular velocity motion definitely cannot be straight line because this is circular motion. Do we understand this, or this is going about it saying bye bye?
Yes, sir.
There it was. Hey, wrong color. The average value and instantaneous value became equal. Here also, average and instantaneous becomes equal. The only thing is one is a vector, the other one is a scalar. That is a problem. As soon as you hear the term uniform circular motion, and this uniform circular motion is going to come in various chapters in different ways. What is the next term that should come into your head straight away? As soon as you hear about uniform circular motion. What is the next thing that should come into your head? Our head is all empty. We empty our head and then come in the school. Huh? The next thing that should come into your mind automatically is time period of UCM. Time period, denoted by capital T. What is this time period? You must know this. Just tell me, what is this time period? Huh? We don't know. What are you talking, sir? Talk sense, sir. What is time period? You heard? You have been using it since your childhood. Time period, time period, time period. Yes. What is time period? Tell me fast.
2 pi by omega.
Okay, what is the definition of time period, bacha? I ask you what is an apple, and you say apple, you eat apple. I'm asking you definition of an apple first. What I do with that apple is a different thing. I might play with that apple. I might not eat it. I need the definition of the apple. You say apple is a fruit, sir. It is sweet, sir, and you eat, sir. You don't say, sir, you eat apple. You don't tell me the use. You tell me the definition. Yes.
The time taken by the particle to complete one rotation.
Well done. That is correct. Time taken to complete one rotation. It could be rotation. It could be revolution. It could be cycle, one cycle. It could be one circle, whatever. Time taken to complete one oscillation, one period, one circle, one rotation, one revolution, whatever you call it. That is your time period. And there's a relation between time period and remember, this time period is only defined for UCM. If the motion is not uniform, circular motion, the time period cannot be defined because at different times it is going to take different instances. It will take different time to complete one circle. So you cannot define time period for non-uniform circular motion. It can only be defined for uniform circular motion. And then there is this revolutionary formula for this. Time period is 2 pi by omega. And from where it comes? Time taken to complete one revolution. 2 pi is the angle it turns in one revolution. 2 pi means 360 degrees. We cannot say 360 degrees because that would be wrong. So it is 2 pi by omega. Do we understand this? Time taken to complete one revolution, one rotation, one cycle, whatever. The SI unit, oops, wrong color. I hate using wrong colors. The SI unit is seconds, it's time. So SI unit has to be second, it is time, so it is a scalar quantity. Don't need to understand this, you know this. As soon as you know that one term of this uniform circular motion is time period, capital T, what is the next term? Term B. The first time you are in the terms of frequency. Frequency. Denoted by small f. What is frequency? Wrong color. What is frequency? Number of cycles or rotations or revolutions per second. And what is the relation? F is 1 by T. But T is 2 pi by omega. So I can write F is omega by 2 pi. Or I can also write omega as 2 pi F. Do you understand this? Yes or no? Omega is 2 pi F. Do we understand this? Huh?
Yes, sir.
These are the relations. Between omega T and F. Everyone should know this. Remember, these are only defined for uniform circular motion. If the motion is not uniform, well, this thing does not right. Now, this omega is definitely your angular velocity. But if you look at what is there in the third equation, what is this F? F is?
Frequency.
F is frequency. What is this 2 pi?
That is displacement, sir. Angular displacement.
So this is angle.
Angle.
So omega is angle into frequency. Angle into frequency. So instead of calling omega as angular velocity, this only holds when the motion is, you are talking about circular motion or you're talking about rotation. What is omega? We'll come across terms, we'll come across the chapter waves, simple harmonic motion and wave optics and all those things. Where omega, where something is not rotating in a circle actually. Something is not moving in a circle, but still we use omega. Now there, obviously omega means angular velocity in circular motion, but even in circular motion, we can call omega by a different name. What is the different name? Omega is definitely circular motion, it is definitely angular velocity, but now I can also call it by a different name, and that name is right now right in front of your eyes. What can I call omega?
Angular frequency.
Yes, we can call omega as angular frequency, and that is the way we would call omega, not in this chapter, but maybe after this chapter when we are done with circular motion and rotation. Omega will become its angular frequency. Do you understand this, or this is gone about it saying bye bye? Bye bye, I'm going. Please don't worry about me.
We understand, sir.
Okay. Then comes this question. A particle completes 1.5 revolution in a circular path of radius 2 centimeter. What is the angular displacement? Huh? .5 revolutions. No one knows the answer? Shall I give you the answer?
Sir,
And the answer? Huh?
pi.
Pi. How did you get pi? Sir, I thought that pi is the answer. How did you get pi? Let me think, sir. Yes or no, sir? Let me think, sir. See, you make your life so complicated. Physics is so simple. It is more simple than life. Physics does not complicate. We must understand how much is one revolution equal to 2 pi. So how much is 1.5 revolution equal to 3 pi? My kid who is in standard 1, standard second, he can multiply 2 by 1 and 2 by 1.5. He doesn't know decimals, but I can make him understand what is 1.5. You cannot multiply 1.5 with 2 and get the answer as 3 pi. Yes or no? You can do this. Do we understand this? Simple things, yeah. Simple things. Please remember them. One revolution is 2 pi. That was the reason I gave you this question. Are we ready for the next one?
Yes, sir.
You should get the answer for this one, sir. One more bad words for you. That does not look good. Chalo, this one. A particle revolving in a circular path. Do it bade aaram se. A particle revolving in a circular path completes first 1/3 of the circumference in 2 seconds, while the next 1/3 in 1 second. What is the average angular velocity? Now this question is similar to a question when he completes 1/3 of the path, 1/3 of the straight line in 2 seconds, and the rest in 1 second. You have to find the average velocity. Here they are asking average angular velocity. Do we understand this, or this has gone above? What I'm saying, bye bye, bye bye, sir, I'm gone. Please don't worry about me. So whatever questions we are doing, Kaveri, is same as what we had done in straight line motion. Same questions. The only thing is velocity gets replaced by angular velocity, average velocity gets replaced by average angular velocity, and there are two more terms that are coming. They replace their respective counterparts. Yes. Answer, bacha. Answer.
2 pi by 3, sir.
2 pi by 3 radians per second. So we have woken up, and that is good. Wake up. This is not the time to sleep. So, how do we do this? Huh?
Total displacement by total time, sir.
Well done. You just have to find total displacement. Why am I writing delta theta? The bug has got on. Average angular velocity, delta theta, total displacement divided by total time. What is the total displacement?
2 pi by 3, sir.
Total displacement is 2 pi, 1 revolution. Time is 1 plus 2, 3. That is your answer, 2 pi by 3. Radians per second. Do we understand this? Yes or no?
Yes, sir.
You can find this one as well and remember it. Just to get an understanding of what the question is asking and what you are supposed to do. You might not get question of this type. It's too simple for you to get, but still, just to get a hang of what we are doing. The ratio of angular speeds. Sometimes in some question, instead of angular velocity, they might call it angular speed. Whenever they use the term angular speed, it means the magnitude of angular velocity. Do you understand this? It does not have the direction sense. Yes, the ratio of angular speeds of minute hand and the hour hand of the clock. Watch or a clock, whatever you call it. Just my dear friends.
Twelve is to 1, sir.
12 is to 1. That is correct. What is the angular velocity or angular speed of minute hand? It is 1 hour. In 1 hour, it completes one circle.
Yes, sir. 2 pi by 60.
2 pi by 60.
Minutes.
What is the angular speed of hour hand? 2 pi by 12 hours.
12 into 60.
So the ratio is 12 is to 1. Yes or no?
Yes, sir.
Okay. Now, we move on to the next heading. And what is the next heading? Next heading, yes. Non-uniform circular motion. When do we say circular motion is non-uniform? Angular velocity changes with time. Non-uniform circular motion. Angular velocity will now change with time. It can change in magnitude, it can change in direction, it can change in both. Now, since we know that this is non-uniform circular motion, now comes the fifth character in the movie. And what is the name of the fifth character in the movie?
Angular acceleration. No. It is also no. Centripetal force.
Average angular acceleration. Average angular acceleration. Alpha, vector, and a dabba. What this average angular acceleration should remind you of? What is this term similar to? What we have already done before from that category.
Linear acceleration.
Acceleration. This is similar to the term acceleration. Similar to the term of average acceleration. Tell me what will be average angular acceleration? Sir, we don't know, sir. What, sir? We are hearing for the first time, sir, and you are asking us, what is this? What is this, sir? What are you there for, sir? Sitting and chilling out. Average angular acceleration, yes. No one knows it. Everyone is thinking, oh God. It is total change in angular velocity divided by total time. Total change in angular velocity divided by total time. As soon as we understand this, it becomes omega 2 final angular velocity minus omega 1 divided by t. The SI unit becomes what? Radians
per second square.
Thank God. You know this. Dimension?
1 by t square.
Chalo. Everything is not lost. Something is there remaining. Good. What is the next term? Now, you must understand this average is always calculated over an interval of time between one point to the next point, between here and there. So this average value is calculated over an interval of time. Yes, what should be the next? What is the next term that comes?
Instantaneous acceleration, angular acceleration.
Instantaneous angular acceleration. Alpha vector. This should remind you of what?
Instantaneous acceleration.
Instantaneous acceleration. And what it actually means is Oops. It is the angular acceleration at any instant. Do you understand this?
Yes, sir.
So I can write this alpha vector as d omega vector by dt. And as soon as we write it d omega by dt, it is the rate of
Change of angular angular velocity.
Rate of change of
Angular velocity.
with time. Do you understand this?
Yes, sir.
Then you can write uniform angular acceleration. When do we say a body is moving with uniform angular acceleration? A body moving with uniform angular acceleration, then angular acceleration will remain
Constant.
same or constant. Yes or no? Then in that case, what will happen, bacha? Your alpha, the instantaneous angular acceleration will be same as what? Average angular acceleration. Do we understand this? It has
Yes,
gone
sir.
above or at saying bye bye, bye bye, I'm going, sir. Most of the cases you will only encounter cases of uniform angular acceleration, but there could be a question where the acceleration is non-uniform. So what will happen in non-uniform? Non-uniform angular acceleration. What will happen in this case? Angular acceleration will change with time. Do we understand this? Yes or no?
Yes, sir.
It has gone above or at saying bye bye. Shall I give you a question now?
Yes, sir.
This is the question, and you have 2 minutes to solve this. The angular velocity of a particle is given by omega is 1.5 t minus 3t square plus 2. The time when its angular acceleration becomes 0 is, you have 2 minutes.
Sir,
Yes, beta.
option B 0.25 seconds.
Option B, 0.25 seconds. That is correct. How did we get it? Omega is given. We will differentiate omega with time. We know how to differentiate it, yes or no?
Yes, sir.
And we just equate it to 0. And we get the time as 0.25 seconds. Anyone got this?
Yes,
I
sir.
don't need to do it now.
Yes, sir.
Okay, then that means I can take you to the next question. Again, remember, all the questions that we are doing are exactly same as what we had done in the chapter on 1D motion or 2D motion. The only thing is velocity get replaced by angular velocity, acceleration by angular acceleration, average angular acceleration by average angular acceleration. Do you understand this? Same
Yes,
question
sir.
can be made in that one as well. The angular position theta of a particle. So if it was linear motion, it was position x of a particle moving on a path varies according to the law r, or x is equal to t cube or whatever, where r is in meters, t is in time. What is the average acceleration of the particle? So the same question. Do you understand this? Nothing has changed. Only angular thing has been put. Find out the average angular acceleration. Time interval is given, and I hope you can do this.
Hello, sir.
Yes, hello students.
Sir, it's 12 seconds. Sorry.
Sir, is 12 seconds.
12 radians per second, sir.
12 radians per second. Let me check the answer. I have the answer. 12 radians per second square should be the correct unit. And how did you get it? Yes. How did you get it? So I have to find out. And remember, whenever we are doing these questions, in the question on 1D motion, we had seen a sign convention. This is positive. This is negative. This is positive. This is negative. Here, what is the sign convention? Here, what is the sign convention? Anti-clockwise is
Plus,
and clockwise is
minus.
okay. Chalo, we have to find out the average angular acceleration. I will not write the vector sign because we will use plus and minus. Average angular acceleration will be omega 2. So omega at 4 seconds minus omega at 2 seconds divided by total time. Total time is 2 seconds. Yes or no?
Yes, sir.
So I have to find omega at 4 seconds. How do you find out omega? We differentiate
Theta.
omega is d theta by dt. I'm not writing the vector sign. I'm using plus and minus. So it will be 3t square minus 6t plus 4. Yes or no?
Yes, sir.
So I now have to find out omega at 4 seconds. So I just put the value of t as 4. What is omega at 4 seconds coming?
28, sir.
28 radians per second. I'm not writing the unit. What is omega at 2 seconds coming?
4, sir.
Just put the values, get the answer, and stay happy. Do we understand this, or this has gone above our head saying bye bye? I'm going. Don't worry about me. Huh? Okay. ठीक है. Now, I'll give you one more question if possible. Okay, ठीक है. Chalo. There is no more question that can be given at this point in time. We have seen all these quantities, right? Now what we are going to see is the equations of motion for angular motion. Equations of motion. Now remember, these equations of motion are only made for what case? For which case? Constant alpha. Do we understand this? Huh?
Yes, sir.
What is the first equation? First equation, my dear friends. First equation of motion for constant angular acceleration. Yes.
Omega 2 equals to omega 1 minus
Omega 2 is equal to
omega 1 plus alpha t.
alpha t. Equation number 2.
Omega 2 square minus omega 1 square equals to 2
delta theta is equal to omega 1 t plus half alpha t square. Do we understand this? Equation number 3. Omega 2 square is equal to omega 1 square plus 2 times alpha into delta theta. Do we understand this? Equation number 4. Displacement in the nth second is omega 1 plus alpha by 2 into 2n minus 1. Do we understand this? Now, if you look very closely, these equations are similar. Are similar to what?
equations of motion in 1D.
For constant acceleration. There the equations was v2 is equal to or
V1
v1 instead of v2 and v1 we were using v and
and
u.
U. V
So
equals
v is equal to
80
u plus 80. Displacement delta r is equal to ut
plus half 80
plus half 80 square.
V square equals to U square plus 2AS
2a into delta r.
delta
Displacement in the nth second will be u plus
U A by 2, 2 in 2n minus 1.
Do we understand this or this is going above or saying bye bye?
Yes, sir.
Now you can use this for circular motion. You can also do this for pure rotational motion. Pure rotational motion is similar to not same to the circular motion. Do we understand this or this has gone above or saying bye 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 sir? I'm going gone. You understand this? Huh?
Yes, sir.
Are we ready to solve questions? Yes or no? No or yes?
Yes, sir. Written all equations.
A particle is moving on a circular path of radius something. Radius 1.5 meter at a constant angular acceleration of 2 radians per second square. At the instant t is equal to 0, angular speed is 60 by pi rpm. What do you mean by rpm?
Revolutions per minute.
Revolutions per minute, not radians per second. What are its angular speed? Means angular velocity. Angular displacement. That is all you need to calculate. Rest of the terms you can neglect right now. We'll do it after we have studied. So rest of the terms you can neglect. You can only do the first two terms. Time is given as 2 seconds. So you just have to find out the angular speed and angular displacement at 2 seconds. I hope you understand the question.
Yes, sir.
Do it. Ja.
Yeah.
Sir, it's done, sir.
Everyone, sir? We understand this? What are the answers?
1 plus 3 pi by pi
Huh?
is the angular displacement.
Let me see. Angular displacement is
1 plus 3 pi by pi.
1 plus 3 pi by pi is how much? Shall I do it?
Yes, sir.
So, the angular velocity at t is equal to 0. That means omega 1. Omega 1 is given as 60 by pi RPM. Yes or no? Now, you have to convert it into radians per second. How do you convert revolutions per second? No, it is not revolution per second. It is revolutions per minute. Do we understand this?
Yes,
To
sir.
convert revolutions per minute into radians per second, what do? We multiply it by 2 pi by 60. 1 revolution means 2 pi. 1 minute means 60 seconds. So you multiply by 2 pi and divide it by 60. Do we understand this? So your answer becomes 2 rads per sec. Do we understand this, or this has gone above what I'm saying bye-bye? To convert RPM into radians per second, multiply it by 2 pi by 60. Now I can find out the final angular velocity. 2 plus alpha is 2 multiplied by 2. The answer would be 6 rad per sec. Do we understand this?
Yes, sir.
When you find out the angular displacement, omega 1 is 2 multiplied by time is 2 plus half, everything is 2. Alpha is 2 multiplied by time is 2 square, and you get the final answer as 8 rad. 8 radians. Is it clear to everyone in the class what we have done?
Yes, sir.
Okay. Now we'll do something very quickly that we already know, and we will just write it again for linear and rotation or circular motion. Remember, we are doing rotation as well as circular together. Do we understand this? The same equation can be made for circular motion. Do we understand this? As well as for rotational motion. Do we understand this?
Yes, sir.
Okay. So this is again the same thing written in a column wise. Do we understand what is written here? Linear motion, and on one side we have rotational or circular motion, whatever you call it. If your linear acceleration is 0, your velocity, initial velocity remains constant. Your displacement, they have written it as s, you can call it as delta ut. If angular acceleration is 0, omega is constant, theta is omega t. Do we understand this?
Yes, sir.
Are you able to understand all the equations that are written here, or shall I explain them?
Yes, sir.
You understand this?
Yes, sir, we understood.
Do you want to note them down? I'll give you 2 minutes, note them down.
Yes, sir, it's done.
Okay. At the same time, you must understand that all the terms are same here. Here we had velocity. We wrote it as v vector. Here instantaneous velocity. Here we have angular velocity, and we write it as omega vector. Do we understand this?
Yes, sir.
All things are similar. Okay. Here, there we have average velocity. We write it as v vector, and that is equal to delta theta. Oh, not in delta theta. Delta r vector by delta t, or you can write it as r2 vector minus r1 vector by t. Do we understand this? Here we have average angular velocity, which we write it as omega in a dabba. Omega in a dabba is delta theta by delta t, or you can write it as theta 2 minus theta 1 divided by t. This was written as dr by dt. This is written as d theta by dt. Do we understand this? Yes or no? Okay. There we have, you can write it as instantaneous velocity if you want to. You can write it instantaneous angular velocity if you want to. Then we have instantaneous acceleration there, which was a vector. dv vector by dt. Here we have instantaneous angular acceleration alpha vector d omega vector by dt. There we had average acceleration v2 minus v1 vectorly divided by t. Here we have average angular acceleration omega 2 minus omega 1 divided by t. Give you 2 minutes to note them down. Have you noted it down? Okay. Let me know once you're done.
Completed, sir.
Okay. Then we have seen linear quantities, we have seen angular or rotational quantities. The next thing is the relation. Relation between angular and linear quantity.
Sir, the screen is not changed.
I know. Sometimes I don't know, but sometimes I know. Relation between angular and linear quantities. What is the relation? Anyone? What is the relation between this linear and angular quantities? Yes, any idea? Now, if you have a circle, we're talking about rotation as well. There is a particle moving in a circular path. The origin is O, radius is R. Now, let us say that he moves from point P to point Q. He moves from point P to point Q. We can find out this angular displacement. We can join this. We can join this. This becomes his angular displacement delta theta. Yes or no?
Yes, sir.
Now, if we talk about how much distance it has moved, what do you mean by distance? Distance is the length of this path. Yes or no? The length of this path is known as the distance traveled. Yes or no?
Yes, sir.
How much is the distance traveled by the particle? This L. How much is that? It is R multiplied by delta theta. Yes or no? Arc of a circle is radius multiplied by the angle. Yes or no?
Yes, sir.
That is the relation between distance and angular displacement. Do we understand this? Distance and angular displacement. Draw the diagram.
Sir, it's done, sir.
Okay. This is the relation between distance and the angular displacement. Now, if I move further ahead, again, same diagram. Again, the same diagram. O, radius R. Now, let us say that he is moving with a velocity. Now, this is the velocity that the particle is having, the original velocity that we called for the particle. The original velocity that we talked about in the motion in 1D and 2D. Now, remember here, there are two directions. Now, when we get into this circular motion or this rotational motion, everything is moving in a circular path. Now, what we had done in motion in 1D and 2D is we defined everything in terms of X and Y, right? Here
Yes.
we are not going to define everything in terms of X and Y because it just looks too complicated. We define everything in terms of radius and theta, yes or no?
Yes, sir.
Radius and theta. Now, similarly to radius and theta, there are two directions that you can call. Instead of having a constant direction X and Y, one direction is in the direction of R. We call that direction radial direction or normal direction. Do we understand this? Radial
Yes, sir.
towards the center. And the second direction is always along the angle. We call it tangential. Do we understand this?
Yes, sir.
For circular motion, instead of using X and Y, we use the other two direction, which keeps on changing, tangential and
Normal.
tangential and normal. So this velocity can now be called as, this is the original velocity of the particle. We can call this as tangential velocity. Do we understand this? Because we know that the particle is going to move and the velocity is always tangential to the path of the motion. Did we tell you this? Did I tell you this?
Yes, sir.
Tangential velocity. Now, if the velocity is tangential like this, it must be rotating like this with an angular velocity omega. Now we can write the relation between omega and v tangential. The vector relation between them is tangential velocity is omega cross r. Now remember, since now we have come to this omega is vector, omega is known as an axial vector. Omega is known as a axial vector. Now, once we know this axial vectors, the problem with this axial vectors is their direction is given by axis. The direction is given by axis. This is a pen. Pen is not a good object. Okay, this one. This is a body kept like this. This is the x-axis, this is the y-axis, and this is the z-axis. You understand this? Now,
Yes, sir.
if I talk about this rotating, remember rotating, it rotates with an angular velocity omega, but I have to tell you along which axis it rotates because omega is an axial vector. Let us say that there is an axis which passes through the center of this. Now, if it rotates along positive x-axis, so I hold the positive axis in my hands. So if it rotates like this, it is rotating on positive x-axis. Do we understand this?
Yes, sir.
This is what axial vector is all about. Body like this. This is the positive x-axis. Rotates. Rotates like this. This is rotation on positive x-axis. Omega is along which axis?
Positive x-axis.
How will it rotate on negative x-axis?
Okay, sir.
If it rotates like this, it is rotating on.
Negative x-axis.
How does it rotate on positive z-axis? If it rotates like this, it is rotating on
Positive.
positive y-axis. How does it rotate on negative y-axis? If it rotates like this, it is rotating on negative y-axis. How does it rotate on positive z-axis? If it rotates like this, it is rotating on positive z-axis. Do you understand this?
Yes, sir.
How does it rotate on negative z-axis? If it rotates like this, you can see this axis here. My hands are the axis. If it rotates like this, it rotates on negative z-axis. Do we understand this? These are axial vectors. They have an axis of rotation. Axial vectors have axis of rotation. All these vectors, omega, alpha, and the vectors that are going to come, they are axial vectors. They are defined by their axis of rotation. Do you understand this? Right now, when I say this omega, how is this particle rotating? This is your x-axis. This is your y-axis. And the outward axis is your z-axis. Do you understand this?
Yes, sir.
So this particle is actually rotating on positive z-axis because it rotates like this. Do you understand this? And therefore, this direction is becomes anti-clockwise on the paper, and therefore we call this as positive rotation. Do we understand why it is positive rotation?
Yes.
Because it is rotation on plus z-axis. Got this? So this is an axial vector. So we take the cross omega cross r. The velocity goes like this. It is very easy to understand. If omega is like this, velocity would be like this. Yes or no? Yes or no? If the
Yes,
particle is here, the velocity would be like this. Yes or no? If the particle is here, velocity would be like this. If the particle is here, velocity would be like this. We understand this?
yes, sir.
So that is the relation between tangential velocity and angular velocity. If we only talk about the magnitude, omega and r are perpendicular here. So the magnitude wise tangential velocity, or people call it linear velocity, becomes omega multiplied by r. Do we understand this? And this is exactly similar to the relation between L and theta and r. L is r theta, L is the distance, Vt is the tangential speed or tangential velocity, or linear velocity is omega multiplied by r. Do we understand this, or this is one above by saying bye bye?
No, sir.
I'm going.
Understood, sir.
Give you 2 minutes to write this.
Sir, it's done.
Then comes the next character. Again, we have this. Again, we have origin. Again, we have R. What comes now? Again, it has an angular acceleration. And let me take, just for the sake of taking it, like this. Alpha is like this. Now, because of this alpha, omega will change. And because of omega change, tangential velocity will change. Yes or no? What changes tangential velocity would be known as tangential acceleration, because this acceleration would be perpendicular to your would be along the tangential direction. Do we understand this, or is it one about what it's saying? Bye bye.
No, sir, we understood, sir.
What is the relation between tangential acceleration and angular acceleration? Again, the same relation, alpha cross r. Both are vectors. Or if you want to write, you can write AT as alpha into r. Now, this tangential acceleration is always either in the same direction as velocity or it is in the opposite direction. So this can only do one thing. It can only change the, and we have done that before, it can only change the magnitude of velocity or magnitude of tangential velocity. Do we understand this? See, if tangential acceleration is like this and the particle is rotating like this with an angular velocity omega, its tangential velocity would be like this. So this will be opposite to your tangential acceleration, and therefore the magnitude of tangential velocity will decrease. Do we understand this?
Yes, sir.
So this is the gentleman that changes the magnitude of velocity. But in uniform circular motion, whether the magnitude of velocity is changing or not, one thing is definitely changing. What is that thing that is definitely changing? Even if it is uniform circular motion. In uniform circular motion, magnitude of tangential velocity does not change. In UCM, tangential acceleration is 0. That implies alpha is 0. That implies omega is constant. That implies the magnitude of tangential velocity remains same. But even if the magnitude of tangential velocity remaining same, one thing is definitely changing. What is changing? Even though the magnitude of tangential velocity in a uniform circular motion, it remains same because alpha is 0, omega is constant. One thing definitely changes.
What will we change?
What is that thing?
Direction, sir?
Direction of velocity changes. And the gentleman that changes the direction of velocity is known as? We don't know, sir. We have come in the town just now, sir. I don't know, sir, anything, sir. What is the gentleman that changes the direction of acceleration? The direction of velocity? You don't know, sir. Better you go, sir, or better you tell, sir.
Centripetal acceleration, sir?
Centripetal acceleration. That is absolutely correct. So now we have an omega. Because of this omega, this is moving. Now we have an acceleration which goes in this direction. Its omega is in this direction, omega vector. Now we always have an acceleration which is, oops, wrong color. I hate wrong colors. Which is in the normal or radial direction. This changes the direction of velocity. and this is known as normal or centripetal or radial acceleration. All the terms meaning the same. Do we understand this?
Yes, sir.
And if I write anything, let me use the word centripetal, or let me use the word normal, because normal, one is tangential, one is normal, you are easy to relate. Vectorly, this is how the direction is. If you want to write just the magnitude of normal acceleration will be omega into v, or you can write it as v square by r, or you can write it as omega square r. This is the magnitude of normal acceleration. The direction of normal acceleration, in which direction it points? It's always towards the,
Center.
and therefore it is known as centripetal acceleration. What is the job of this normal acceleration or centripetal acceleration? The job is to,
Change the direction of.
the job is to change the direction of velocity. Job is to change the direction of velocity. And now we come to our old hero, normal acceleration A. This acceleration can change the magnitude, this can change the direction, this can change both. Therefore, it is the vector sum of an plus at. Do we understand this?
Yes, sir.
Magnitude wise, if I call this, it will be root over an square plus at square. Do we understand this? Do we understand this, or this has gone above it saying bye bye?
Yes, sir. We understood.
This is known as normal acceleration because this is always, my dear friend, this is perpendicular to velocity. Do we understand this?
Yes, sir.
This is known as tangential acceleration because it is same direction or opposite to velocity. If it is in the same direction, Vt ka magnitude increases. If it is in opposite direction, Vt ka magnitude decreases. Do we understand this?
Yes, sir.
That's all that you need to remember. This is the entire motion in 1D and 2D put together. If the body only has tangential acceleration, no centripetal, the motion would be straight line. If it has no tangential, only centripetal, the motion will be UCM. If it has both centripetal and tangential, the motion is general motion. Do we understand this?
Yes, sir.
No tangential, no centripetal, straight line. No tangential, only centripetal, UCM. Centripetal as well as tangential, any motion in this entire universe. Got this?
Yes,
With
sir.
this, we end this class. In the next class, we'll take more steps and do things from the previous chapter, work, power, energy, as well as we'll step into the new chapter. And if you understand these terms, life becomes very easy. So I'll end this class here. I hope you have enjoyed this class and you have learned. Please go through this. I've already sent you the sheets. Start working on those sheets because there will be questions what we have discussed in those sheets. Okay? So do that and I'll see you in the next class tomorrow. Take care. Have a nice day. I hope everyone has noted this down. Yes or no?
Yes, sir.
Okay. God bless you all.
Thank you, sir.